Well, let me go ahead and get started then with our keynote by Marianne Piette, Decarbonizing the Building Sector and Integrating with a Clean Grid. There isn't anyone better to do this high-level overview for us than Marianne Piette, who has 35 years career at Berkeley Lab. I've known Marianne for 20 years and been working closely with her for the last 15 years. And it's always a tremendous joy and honor to work with Marianne and to introduce her this morning. She's now been given a lot more workload, so she's now been elevated to you're now an interim.
Associate
Are you still
interim associate lab director? That's right. Yeah.
Okay.
And I'll make a couple of comments about that.
Okay. And again, thank you so much, Marianne, and we're looking forward to your overview.
Thanks, Peter. Can you see my slides okay?
Yes.
Great. Well, I want to thank you for the introduction, and it's a great pleasure to be part of today's program for the BEST Institute and helping to create materials to improve the workforce for the building decarbonization strategy. As Peter mentioned, I'm the interim associate lab director of what's called the Energy Technologies area at Lawrence Berkeley National Lab, and I'll be sharing a number of comments with you. As the ALD, I work across a broad portfolio of technologies beyond buildings, including hydrogen, electric storage, carbon negative technologies for carbon capture, critical materials, desalination, and a variety of things. So I'm enjoying learning a lot about a broad portfolio at DOE and LBL. I'm going to give you a quick introduction into U.S. climate goals. We'll talk about the strategies for building decarbonization and future directions and emerging technologies and challenges. So it's an important topic. The United States has a lot of different climates, a lot of different end-use loads, and so many different types of electric grids and power systems. So it's a big topic, and I look forward to providing you these comments. I'll stop about 10 till the hour to make sure we can have some Q&A in my comments. Let me talk about what the U.S. goals are. The U.S. goals are to reduce the greenhouse gases by 50% by 2030 versus 2005 levels. So we have a very aggressive goals to reduce the emissions in the economy overall. We want to have net zero emissions by 2050. So again, cut emissions in half by 2030, zero emissions by 2050. And that 2005 is the baseline, and I'll show you some of that data in a moment. One of the key ways that we want to do that is by decarbonizing our power systems with renewable energy, 100% carbon-free electricity by 2035. And then on the right there, we need to do this in a way that makes sure that 40% of the benefits are flowing towards disadvantaged communities. And those disadvantaged communities are communities such as low income or areas that have poor air quality. So there's a variety of ways we think about the energy justice portfolio and how important that is. Sorry about that. I'm got my slides here. Now I'm having trouble with my slide here. This is a picture of the US and our current emissions over the last few decades and projected out into the future. So you'll see historically, this is in gigatons of carbon dioxide emissions. We had very high levels around 2005, and we've been measuring the reduction since 2005. So we're 17% below 2005 now. If you look at the recent data, it sort of goes up and down. It went down to the pandemic and up a little bit again. But we want to make sure that we're at 50% by 2030, as I mentioned before, and then all the way to net zero by 2050. So these colors are the various targets. But this is basically the concept of joining the Paris Agreement, and that aggressive reduction that you can see on a time series graph here and what that looks like. Now, when we move to the building sector, there are basically, I tend to think about three main sectors here, but we also have agriculture, which is often included in industry. So commercial buildings are about a third, a little bit more of the total emissions, 27% from transportation, 30% from industry, 11% from agriculture. And when we think about buildings, the emissions are related to the direct consumption of fossil fuels, so burning natural gas for space heating and water heating and cooking. And then that light blue there, 19% emissions from indirect power from the electric grid. And we also see fluorinated gases and things like your refrigerants, and then landfill and waste services. So these emissions are all important for us to reduce, but you're going to see we're going to really focus on that 9% of the fossil combustion, and then the direct power emissions, integrating buildings with a clean grid with more renewables. So we're going to spend a moment on this graph to show you the way we think about buildings that are central to multiple decarbonization pillars. On the very left is the concept of connecting the building with EVs. The building is now on the meter. You're going to see transportation loads. So we have kind of an accounting challenge, but we want more buildings to use electric systems, and we want to make sure that we're charging at the workplace during the day and charging at home. We need to integrate with the grid, and I'll talk a little about that later, but we need flexible loads and distributed generation and storage. So the building's part of this emerging clean electric system. At the top, as I mentioned, we want to reduce fossil-fired demand through energy efficiency and electrification of heating, water heating, and cooking. We want to limit the scale of electricity infrastructure needed under grid decarbonization. So energy efficiency helps us with our existing electric system to build a smaller one. We don't need as much wind or as much solar or as much geothermal if we have energy efficient buildings. And that's a really important thing we have to remember. Energy efficiency is often the first line and one of the most cost-effective ways to reduce carbon emissions. And of course, then we need to make sure that we're doing these things with an eye towards energy justice, community resilience, and resilience might be a resilient grid for power outages or resilience to extreme heat and extreme cold. We want improved air quality, improved health, and energy security. So energy security, if we go back in time to the oil embargo, we were buying foreign oil and we found disrupted markets, and energy efficiency activities at Lawrence Berkeley Lab and around the country were spurred because we realized that if we used less energy, we would reduce our need to import foreign sources of energy, which is what's happening in Europe right now. So energy security is one of the most important things when we think about energy efficiency, that the Europeans are struggling with that, to have less Russian sources of energy. And in general, energy efficiency really helps economies to have more security in their energy systems. Now I'm going to go through some of the concepts related to, related to strategies for decarbonization. 4 key strategies: energy efficiency, as I mentioned, integrating with the grid and grid services, using more distributed energy resources, and electrification. So energy efficiency, I said, lowers the need for having a clean grid. We can have a smaller grid if we're energy efficient. Grid services mean that we want to integrate with the grid. Now, the grid is challenged by something called the duck curve, and at certain times of the day, electricity is cleaner, and at other times of the day, it's dirtier. So we have a lot of solar in the middle of the day. So on the left, you'll see shedding load and shifting load. Energy efficiency means we're bringing the whole energy load shape down. Shedding load is often important at peak times on a hot summer day or a cold winter morning. So we want to change the way we're using energy in the building for 2 hours, 4 hours, 6 hours, something like that. Shifting load is shifting that load to another time of day, which might be something we do every day, or it might be something we do that's dynamic depending on what's happening with the grid. So things like heat pump water heaters may be a shiftable load, and you really want to try to avoid using that energy at peak times. In California, the electricity price is high from 4 to 9 p.m. After the sun goes down and we have more conventional energy sources that are dirtier, that 4 to 9 peak is one of our challenges. Distributed resources mean enabling the ability to connect with batteries, photovoltaics, and EVs, and then electrification. These are a set of things that are 12 core strategies when we think about building technologies that we care about. Energy justice, I've mentioned. Workforce, this entire 3-day institute is about workforce, making sure that we're creating understanding and new knowledge around what kind of workforce do we need to make this transition to low carbon building sector. We care about healthy indoor environments. We care about community resilience, reducing energy cost burden. So many people have trouble affording the heat or air conditioning, and we really want to improve the ability for people to be comfortable and healthy in their homes. We do that with efficient equipment and electrification. So we have people-centered technology, energy efficiency, and then clean systems, integrating with demand management, the clean grid, material life cycle emissions. You're going to hear a little from Avon today about material life cycle emissions and low global warming potential refrigerants. We need refrigerants that are good for the atmosphere and have lower emissions and reduce the global warming potential that a lot of refrigerants have. So that's a portfolio of research to do all of these 12 things. And we're doing a lot of that work at Lawrence Berkeley National Lab, as well as many of the other national labs, collaborating with ASHRAE and other organizations. Now I want to get into a little bit of the data themselves. This is a plot from Jared Langevin. You'll see here a business as usual reference case in black. And this is the emissions over time for the building sector. We want to electrify to reduce from about 13,000 CO2 emissions in million metric tons of CO2 down to about 11,000 by 2050. In the green there, we have moderate electrification, decarbonization, energy efficiency. And then in the blue at the bottom, the most aggressive scenarios. So it's technically feasible to reduce 90% of the emissions by 2050, but that's a big challenge. And we have to put the workforce in and the technology portfolios to do all of the things that are important. In the bottom are the colors of the different end uses we evaluated: HVAC, water heating, electronic loads like computers and electronics, cooking, refrigeration, lighting, washing and drying, ventilation, and trying to understand how's the envelope influencing this. We need to make sure we put in good windows and insulation that reduces those HVAC loads. So we have a portfolio of technologies and we model the pathways to decarbonization. Now, when we think about electrification, let's see, I lost my header there. We really care about how many homes do we need to electrify. And what you'll see here is 25% of the homes are already all electric. So you'll see up in the Pacific Northwest, all that green, there's a lot of electric, both heat pumps and electric resistance heat. We want to move towards heat pumps as much as possible, but we already have a lot of all electric buildings. 40% of the homes have electric primary heating. But you'll see there fuel oil up in the Northeast, LPG in many parts of the country, natural gas. throughout the country and other sources of heat. So this is what it looks like today. And we want to move that to being that dark, light green as much as possible. So as I mentioned, there are many electric end uses in homes. Of course, most homes use electricity to condition for cooling, for air conditioning. 64% of the homes today, or that was in 2015, use electricity for clothes drying. There's a lot of electric cooking, but the biggest users are these water heaters and space heating. So less than half of the United States uses electricity for water heating, and about 30% use it for space heating. So this is what we currently have in homes, and we're going to look at what is it going to take to decarbonize and electrify homes. You're going to hear more later today from Ian Walker about this, but here are some of the data on what does it cost to get to electrify and decarbonize homes. In the bottom on the x-axis is percent carbon savings. So we're looking at a 50% retrofit. What does it take to cut the carbon savings in half in homes? Well, it's taking about $20 to $30 per square foot. It's taking much more in California, and it takes less in other parts of the country. But you'll see there, we've been collecting data on estimating the cost of decarbonization retrofits. And a couple of the barriers are important. One of the barriers are rewiring and upgrading the electric service. In most homes, existing homes, the size of the capacity of the electric system doesn't allow us to put in a large heat pump for space heating, a heat pump for water heating, and maybe an EV. So we may not have enough panel service, and we want to explore how we can reduce the cost to the wiring upgrades. Homeowners are really challenged by hiring the contractor and figuring out what to do those retrofits. So we need to reduce the time and the effort for homeowners to coordinate that. And we need to motivate owners and provide access to capital for those retrofits. So those are an important part of the portfolio. And I wanted to share some really interesting technology. As mentioned before, we need energy efficiency, but we're also introducing this concept of what's called power efficiency. Energy efficiency means you're getting the most service for every kilowatt hour. So we understand what an efficient light bulb is. But power efficiency means we're getting the most service for every kW. So these things like smart circuit splitters and circuit sharing, so you can plug in your EV and your heat pump on the same circuit, and you make sure that EV and that heat pump aren't running at the same time. So we have devices that are helping us to take the power into the building and to be able to share it for different loads. Programmable sub panels. You're going to hear some of this from Daniel Gerber today. And power efficient appliances. So we also use the term low watt diet. Sean Armstrong from Redwood Energy is looking at how we have power efficient devices in our homes and get those services with the minimum power upgrade for our service panels. We're looking at things like the LG water heater, which is a condensing washer dryer combination device, heat pump water heaters that are 1 kilowatt, and through the wall heat pumps. So there's a variety of new technologies that help us to have power efficient technologies for home retrofits. Now I'm going to talk a little about integrating with the grid. Why do we need grid interactive efficient buildings? What's happening is we want to have more renewable energy, and that energy is variable. So as we move towards more solar and photovoltaics and wind in the grid, that energy is not available all the time. So we want loads to be able to use more of that energy when it's available. We want to reduce the costs of our aging infrastructure and make the grid more reliable and facilitate decarbonization through more renewable integration, but make sure customers understand and are valuing the interaction with their devices. So we want to optimize energy use based on customer preferences and understand the people side and the behavior of these technologies. there are a couple of, I'm going to make sure its graphics are working correctly. There are 4 key things we think about for grid interactive efficient buildings: energy efficiency, which I've talked about, and then connecting. The devices, we want them to be smart and connected. We want communications with the devices, and we want the devices to be able to understand the outside air temperature, the price of electricity, who's in the building, and to be responsive and flexible so they can shift and shed and reduce their load and integrate with the grid. Now, when we think about grid integration and the electricity savings, we created something called the GEB roadmap. So we have a national roadmap for grid interactive efficient buildings. So that's gebroadmap.lbl.gov. And we worked with several partners around the United States, and we actually modeled how much CO2 we could save by making the buildings more grid interactive. This savings is about equivalent to 50 medium-sized power plants by 2030. So if we can reduce the energy use, make them more grid interactive, we can save about 50 medium-sized coal power plants or 17 million cars. But the savings we get vary by region. So when we save a kilogram of CO2, we save a lot in the dirtier parts of the country, that like the upper Midwest, lower Midwest, and the Great Lakes. They have more coal in their electric system. So saving a kilowatt there saves a lot. In California, the grid's already pretty clean, so we don't save quite as much per CO2 per kilogram of megawatt hour saved. So we have variations around the country, and that's really important when we teach students about electrification and what's happening with the grid, that the grid's different around the country and everything matters, but we're going to save a lot of CO2 in certain parts of the country with these retrofits. Now, I want to share with you a little bit about something called the duck curve and integrating with the grid. On the left is a day in California in May where we had a record amount of renewables on the grid. So we had 2 records in California this year that are important. The light green there is the total load of all buildings, all EVs, all industry. The orange is the net load, and that is the electricity minus the renewables. And then the green is we actually generated more renewables than we could use. So I have a couple of arrows here. So nearly 100% of the load on that day was met by renewables. And that was a record for the amount of wind and solar that was available on a given day. These days happen in the spring where there's not a lot of cooling load, but there's a lot of solar. So these days had significant excess generation exported or curtailed. And we also had this ramp. Now the ramp is a problem because the grid operators are supplying, they're supplying about 15 gigawatts in the middle of the day, but around dinner time that gets up to 25 gigawatts. And we had plenty of solar, but we had this net load ramp in the day, and it's very difficult to maintain the grid when we have these big swings over the day. So it's very exciting that we had high levels of renewables, but we have to integrate the buildings to make sure that we're reducing the need to curtail. So that energy use in the middle of the day, we couldn't even use it, and we were exporting it out of California. On the right was the highest grid consumption ever in California. So we had load forecasts that exceeded the available capacity. But what happened was demand response was called. So we actually thought there were going to be rolling blackouts. We used over 52 gigawatts. And you can see the grid that we peaked around 3 in the afternoon, but the net load peaks later in the day because as the sun goes down, we have less renewable energy, and the net load peaks late. And that's that 4 to 9 period. So we want to be able to curtail load on these hot days, and we have a variety of technologies that we can do that with, and I'll share some of those in a moment. But it's really important to understand what's happening with the grid and how we want buildings to be able to integrate with this changing renewable grid. At around 6 p.m., the state called almost like an Amber Alert, and there was a cell phone emergency call. So we dropped about 1.5 gigawatts from people turning things off, turning off all your lights. Some people unplugged their refrigerators for an hour or two. There were rolling blackouts at some of the small municipals that thought that they were being asked to curtail. We almost lost the grid in California, but we kept it up, and that cell phone emergency alert was never been used before, but it actually significantly reduced the grid. So to emphasize this a little bit more, I have this picture here for you. We have something called CalFlexHub. I'm going to spend a few moments talking about that before I wrap up. The California Load Flexibility Research and Deployment Hub is developing technology to enable the use of electricity prices to adjust electricity use and greenhouse gases. And see in this picture here, I showed you that kind of duck shape. And in the middle of the day, grid is cleaner. And we're trying to make sure that with dynamic prices, it's also cheaper. That around 4 to 9, when the sun goes down, the grid is not as clean and the rates are more expensive. So we're moving towards a time where we want to be able to use prices to actuate dynamic loads that are listening to price signals and changing their shape. So we're exploring in CalFlexHub how to use these signals to communicate electricity prices that are changing every hour and greenhouse gas information. And we also are trying to make sure that we promote equity in doing this kind of work. We're working with the state of California to develop something called the Market Informed Demand Automation Server. So the state actually has a database of electricity tariffs and one portal where we're allowing customers and aggregators and technology vendors to come and get prices that are sent to devices. So again, we're using prices to devices, working with utilities, community choice aggregators, and that RIN is something called a rate information number. So you'll have a specific a rate identification number that allows you to make sure you're listening to the signal that reflects your electricity tariff, your devices, and that your devices can be programmed to respond. We're also exploring the use of FM broadcasts. So whether you're using a FM signal, now that's very challenging. It's actually there's not a lot of devices that can listen to FM. It is one of the things we're looking at, but most of the signals are coming through the internet, and they're using your own Wi-Fi to get these signals. So we're working with the state of California on something called load management standards. Here's a picture of what some of that communication system might look like. Well, we're working with a company called Olivine that has developed a price server to send out these dynamic prices in a form that's easy to understand. The CalFlexHub price server would go to a control logic platform. And the concept here is some smart thermostats can respond to traditional demand response signals. So they know how to pre-cool. But what we're trying to do is be able to send 24 prices day ahead, a temperature forecast, and some idea of the user's comfort parameters. So people could say, I'm willing to let my house go up to, say, 78 or 80, and I'm willing to pre-cool down to maybe 68 or 70. And we're going to use the mass of the home and create a set of optimization signals that turn the prices into a control signal. So we're working with Ecobee and Olivine, and we're working with a number of vendors. In CalFlexHub, we have 18 different partners working on technology, working with homeowners, working with disadvantaged communities, and a variety of other systems to get this technology out and understand how does this work in both commercial buildings and in larger buildings. This is one example of some work we've been doing at UC Merced. UC Merced has 4 megawatts of on-site solar, and it has a very large chill water tank. So you can see here in the baseline, they actually send some of their electricity back to the grid, but using something called model predictive control, we're using their own on-site solar and the grid to improve the use of their own self-generation, reduce carbon emissions by 10%, as well as reducing peak demand charges. I think I have one more. There we go. About 10 to 15% of demand charges were reduced. So we take a control system that's looking at the price of electricity, the availability of their own on-site solar, greenhouse gases, and the peak demand charges. So we want to make sure that when we do these things, we're reducing the bill. So we've been able to save around 1 metric ton of CO2 per day, which is equivalent to driving a car across country. And that's for 1 day of changing the way they're operating and integrating. Normally, thermal energy storage systems are used at night, but we've been integrating this and actually controlling this TES to be charged in the middle of the day when it's cleaner. And that's a very big change for things like thermal storage. And thermal storage is an important type of technology that the US Department of Energy is making a significant investment in for a clean grid. The CalFlex Hub is doing a lot of work on many different building sectors: single family, multifamily, small commercial, large commercial, and campuses, as I mentioned. And we're working with heat pump water heaters, heat pumps for HVAC, a lot of work on software and controls, because as mentioned, these technologies are available, but they can't take this continuous price signal. So we're working with pool pumps, electric storage, as well as thermal storage and EVs. And we're doing a series of hardware retrofits in many homes, in multifamily buildings, and in small buildings. And the picture on the right there shows a building which calls the HP Flex Cloud, where we're showing the control system needing to coordinate with the EVs, thermostats, storage, and heat pumps. So we're trying to understand the control systems, and Marco Bertoni will be talking about this to share with you the kinds of control platforms that are being developed for us to retrofit controls that can take these price signals and be able to reduce the bill, reduce the carbon footprint, and integrate with the grid. I have 2 more slides before I finish off here. This is equity and load flexibility was the subject of a webinar that we had earlier this year, and we had the CalFlex Hub program. And what are we doing to help disadvantaged communities? We had Matt Fung, who's works at the California Energy Commission, working with us, as well as Megan Chin with the Association for Energy Affordability. The Association for Energy Affordability is doing fascinating work related to understanding how low and moderate income households might interact with these technologies. And there's a pilot in the San Joaquin Valley where they're retrofitting LPG water heating with heat pump water heaters and making sure those water heaters can respond to signals. And sometimes they don't have an FM signal. They may not even have cell service. So it is very difficult to get communication into some of these homes that don't have those technologies. And we had Alejandro Castellan working with the Bay Area Association and the Rising Sun Center for Opportunity. And Alejandro was talking about work that Rising Sun does in disadvantaged communities, helping them with smart thermostats, window retrofits, and other devices, and energy efficiency, and helping people understand if they change devices in their home, they can save money on their bill. And Nicole Hannes from LBL is working on creating materials for electric utilities to value equity investments and disadvantaged communities in the traditional utility portfolio cost effectiveness calculators. So we need to really understand how to interact with these communities. This is my second to last slide. I want to make a couple of comments about training. I've made a number of comments about technologies. We need to understand how to accelerate the workforce related to designing and installing heat pumps, we need to understand how to install and configure grid communications and controls. And I've given you a little bit of introduction into price communication and demand response communication. Things like OpenADR and MIDAS are new terms for people, but these technologies are coming with utility programs, and utilities are also subsidizing integrating EVs, photovoltaics, and sizing and controlling storage. How big of a battery should I put in? How big should that thermal storage system be? And we want to also understand greenhouse gas benchmarking. You're going to hear a little bit later from Joshua Case around building performance standards, and that is about benchmarking GHG in buildings. So my final slide, I want to emphasize that there are numerous pathways for decarbonization. I mentioned energy efficiency and electrification. We want to reduce the use of greenhouse gases for space heating, water heating, and cooking. We want to integrate buildings with the grid. And the picture here shows the concept of moving from historic static energy efficiency to dynamic energy management, integrating with distributed energy resources, and thinking about the training needs in this portfolio. So I'll stop there. And I do see one question in the chat, and I'll stop sharing with my slides here.
So Marianne, thank you so much for that broad overview. My question was, how California-centric is this work with grid interaction? And James Horst from Delaware indicates that load shedding is being used by his utility in Delaware. And I'm just wondering, how quickly is the work in California diffusing nationally? How many states or local utilities are actively engaged in load shedding work and grid management work?
I'd say about approximately a third of the country has demand response programs. So demand response programs traditionally are focused on the hottest hours of the year, those top 200 hours. What we're doing in California with price response, we're trying to think about 87, 60 hours, every day, every hour, because the grid is constantly changing. And that's the biggest change, is moving from traditional hot summer DR or cold winter morning demand response. Some areas have cold winter mornings, but moving that to this continuous integration with the grid. So that's the main thing, is that that's a very new concept. There are utilities that are working with bring your own thermostat programs or bring your own battery, but they typically don't have a continuous signal. And we're trying to move towards that continuous integration for EV charging, battery integration, and control integration.
So we have an interesting comment from Robin in upstate New York.
She's concerned about it being dependent on natural gas.
Yes. Maybe you can comment on his.
Yeah, well, I want to emphasize that clean natural gas consumption is still important. So when you put in a furnace or a gas water heater, I want to emphasize something, Peter. The grid in California is different than the grid in Ohio. So putting a heat pump in Ohio is less important than putting it in California, because the grid's dirtier there. And for example, an EV in California saves a lot more emissions than an EV in Ohio, as an example. So the grid, I showed you the savings in CO2 per megawatt hour. I showed you different regions of the country are different. So we have to have some nuance in this discussion. As this person points out, that the grid is not the same everywhere. And that's one of the challenges as we educate the workforce and we talk about electrification and decarbonization. It's not the same in every part of the country. So that is one of the challenges, is understanding the local context for the electric grid and what is. The states are developing renewable portfolio standards. And that's an important thing, is to understand what is happening in your state, and how do you facilitate decarbonization in your state, because they're very different.
Michael Bobker in New York City has a question.
Yeah, I see. He's asking about, does it effectively capture all of the intermittencies in the grid? Is there parallel work being done on frequency and voltage? So you know, we talk about 4 grid services: shape, shift, shed, and shimmy. And shimmy is the really fast acting voltage and frequency response. I have not talked about that in this price response context. The frequency and voltage response is fast acting controls. VFDs actually can be frequency responsive, but it's very expensive to install that kind of control. So there are very advanced grid integration concepts that Michael's alluding to here. And it's true that there is work on that topic. Batteries are pretty good. Electric batteries are pretty good at frequency and voltage response. And there's also something called conservation voltage reduction, where utilities are looking at actually what voltage are they providing you, and can they tune the voltage to save some energy? And they can do that dynamically or as more continuously. So have a particular voltage. So the voltage on the grid varies depending where you are on the grid. So there's a lot of local control. And what's going to happen, Peter, is that your substation and your distribution system are going to become a lot of where the action is. I showed you statewide kind of data, and we talked about states and we talk about regions. But as the grid gets cleaner, what's happening to your local distribution system is going to matter, because if everybody in my neighborhood has a Tesla and plugs it in at the same time, my distribution system and my local substation can't handle that load. So we have a lot of work that's going on that's going to happen very local. And the EcoBlock showed us some of that yesterday, that your energy management is going to become very local. We're not quite there yet, but when we electrify, we're going to have a lot of changes in our local substation and distribution system control. Some people are looking at local prices that actually have a distribution system adder of some sort, but we don't have that controls and communication yet.
So we have time for maybe 1 or 2 more questions. Ted in Wisconsin asks, do you know where the 40% of benefits from federal climate and clean energy investments flow to disadvantaged communities? Where does that come from, and how do we access funding to support disadvantaged communities?
Yeah, that's a really good question. I have two answers for one. One is Shalonda Baker is the head of the Justice 40 program at the Department of Energy. And I could look at for the website and send it around later, Peter, but there are community-based activities. Yesterday, Shreyas Jatkar mentioned some of the things that they're doing where the community-based savings are going to be part of responses to federal solicitations. So they're sort of peanut buttered across a lot of the new IRA funding and things like that. There will be some local disadvantaged community requirements in many of those solicitations. There's something called Clean Energy to Communities program that the Department of Energy is going to be launching with technical assistance to communities. So I can try to find a few links to some of those, but they are available. And if you Google Shalonda Baker's office at DOE and look for some of that, you'll see some of the activity there.
Great. I guess we can, if you'd like to comment on Robin, and that'll be our last comment.
Yeah, Robin is asking about, we haven't talked about embodied energy and the energy in the infrastructure for these clean things. I've heard that if you put solar panels on your home, the embodied energy in those solar panels is, it takes about 1 to 2 years of operation to make up for the embodied energy to build those things. So that means you got another 15 plus years of savings to make up for the embodied energy. So it's a good point. There's embodied energy in the steel for the wind turbines, for all of that, those batteries. There's a lot of energy in those batteries. We're trying to make the batteries more recyclable. So it's an excellent point that there's embodied energy in this infrastructure. However, over the life cycle of those systems, they are net positive for the economy and for our energy infrastructure. And they, if you compare that to the emissions from coal power plant, these things are going to save us that. That's why we talk about net carbon by 2050. We want net carbon-free grid by 2050. And we want to consider all those things as well.
Well, I think we're going to end it there. Thank you so much, Marianne, for an excellent overview. And you're one of the nation's premier grid interactive experts, and we so much appreciate you. We're going to shift to our next presentation. And thank you for those excellent questions as well from the field.
Yeah, great questions. And thank you so much, Peter, for the opportunity to speak to these participants today.